Okay, so now we're ready to look at actually how we're going to place these vortices on the wing for this numerical lifting line algorithm. Now, let's just recall really quickly what we did for the classical lifting line algorithm. What happened there is that we said we had this lifting line, which we placed along the quarter chord of the wing, and it varied. Its gamma value varied as a function of z. Okay, so we had z along the wing here. So gamma varied as a function of z, and and the change in gamma was related to the vortex strength of a sheet at any location z. Okay, so those two were related, and so we basically just placed actually as a continuous function. We didn't place these as individual vortices, but we can think of them as individual vortices. But really, this is a sheet of vorticity here in the wake, and then some continuous function of capital gamma that moves along the quarter chord here. So what we're going to do with the numerical lifting line algorithm is we're going to try to draw a wing here with some dihedral and sweep. You can imagine that the sweep is easier to draw than the dihedral, but anyway, what we're going to do is we're going to place, so we're still going to define our quarter chord here, and then we're going to place a series of horseshoe vortices that extend from infinity and then come up across the wing a certain distance and then extend back into infinity. Okay, we're gonna do a whole bunch of these along the wing. So this is a series of horseshoe vortices that will look something like that. Now I haven't drawn these very well, but you can imagine this is in the direction of u infinity here. And so we'll just continue putting those across the wing. Now I've drawn those with a gap here, but that's just for visual purposes. Actually, in reality, these are going to butt right up against each other so that the trailing vortex of one horseshoe vortex is coincident with the trailing vortex of the neighboring horseshoe vortex. Okay, so actually those will overlap and be coincident at those locations. Okay, so so each of these horseshoe vortices is going to have a strength gamma. All right, so it has some strength gamma, and we'll say this is gamma I for this ith vortex. And actually, we're going to draw this horseshoe vortex according to the right-hand rule. So actually, the direction here of this vortex is such that it comes in this direction and leaves in the opposite direction here, and has a direction along the quarter chord in that direction there. Okay, so it is so it's inducing velocity in this direction along its length. Okay, so that's our horseshoe vortex I, and now what we need to know is how much velocity does that horseshoe vortex induce on any other point in the flow. Okay, so let's just take one of these horseshoe vortices and zoom in on it here. So we've got a direction there, direction there, direction there, strength gamma, and then we want to know about the velocity that it induces on some arbitrary point. But we know the geometry or how that point is related to that horseshoe vortex. We're going to define a R1, just like we did before, and an R2 that go from the two corners of this horseshoe vortex to that point of interest. And then, of course, the direction here is just u infinity. We know we're going to allow these to go in the direction of the free stream. Now, I should go back here to the original classical theory. What we did with this trailing vortex sheet was we had that aligned with the x-axis. Okay, so it was right on the actually on the xz plane in the direction of the x-axis, which is really close to the direction of the free stream velocity, but not exactly the same. And the reason we did that was because that simplified the math so we could get this analytic solution, okay, for that classical theory. Well, when we're working with this numerical algorithm here, there's really no benefit in aligning these horseshoe vortices with the x-axis instead of just with the free stream. And they're going to be aligned with the free stream eventually. So if we go really far downstream behind this wing, we'll see that the wake of this wing really aligns itself with the free stream velocity. And so we're just going to assume that each of these horseshoe vortices, or the trailing portions of them, must realign with that, with the free stream velocity, and we're just going to put it in the direction of the free stream velocity. Okay, so we're going to call these the trailing vortices, and then this region here is what we call the bound vortex. That's the portion of the vortex that is bound to along the chord. We're gonna put the bound vortices along the local chord, which is aligned with or dependent on the sweep and the dihedral of that wing. So we're going to place those right along there, and that's called the bound vorticity. Okay, that's the portion that's bound to the wing, and the trailing vortices are aligned with the free stream. Okay, so from our previous development for the influence of, in fact, I can just scroll back up here for the influence of some vortex segment on some point. So we can look at the induced velocity at a point by some vortex segment. We came up with these two different equations. This equation here is for can be used to compute the bound vorticity influence. So if we imagine that this is the bound portion of the vortex, this is the velocity that will be induced at some point by that bound portion. And then this equation here is the equation that shows us what the induced velocity will be from one of these trailing vortices that goes off in the direction of u infinity. Okay, so we can just combine this equation here with two of these, because we have two trailing vortices, to get the total induced velocity by this complete horseshoe vortex on a single point. So I'll just write that out here really quickly. So the total velocity induced on some point is going to be equal to the strength of that vortex divided by 4 pi times u infinity cross r2 over r2 times r2 minus u infinity dot r2, and then plus, okay, so this is the influence of the one trailing vortex here on the right hand side, okay, and then we're going to add on the influence of the vorticity on the left hand side, and this actually has an opposite sign because gamma is associated with a certain direction here, right? So positive is in this direction, and so we actually have to flip the sign on the second guy, which I forgot to do here. So that will actually be a negative minus u infinity cross r1 over r1 times r1 minus u infinity dot r1. Okay, so those are two trailing segments, and then the bound segment is simply r1 plus r2 times r1 cross r2 divided by r1, r2, r1, r2 plus r1 dot r2. Okay, so this is the total induced velocity from this horseshoe vortex on some point. That can just be an arbitrary point. All we'll have to do is figure out what r1 and r2 are to that point, and then plug those into this equation, and we can calculate the induced velocity from that horseshoe vortex.